Okay, good morning, everyone. 2/3 of the course done. 3 days done, 1.5 days to go. We didn't finish the diagnostic testing yesterday. However, I feel that maybe it would be not the best use of our time because I'm afraid then maybe we will discuss that too long and then rush through the VAR and the VEC-M and the ARDL and the gauge. So what I want to do at this stage is just to refer you to this error correction modeling lecture and diagnostic testing, and you will see that there is a summary file there that's actually also discussed. I've narrated this file, which basically provides that bird's eye view on what we do when we do diagnostic testing, and this is discussed, and then the details are in that 50 slides or so of the diagnostic testing. So I would rather, because the same things basically applies to whether we run Engel-Granger co-integration or whether we do an ARDL or a multivariate VEC-M, the diagnostic testing in general applies. So I will, in other words, we will come back to this after we finish the VAR and the VEC-M and the ARDL. And also the other topic that we skip at this stage is the other unitary testing, where we add all those other, the GLS, the Dickey-Fuller, the ERS, the Ngunparon. So all of that is discussed here, but also for that, if we go under, if we go to the examples, the practical application, to the practical application, this example here, example 2 on the exchange rate, contains a discussion of exchange rate, the exchange rate theory applicable here, and then inside here are also narrated material on all those unitary tests, how to apply them, and also the additional how they are different to the Dickey-Fuller. So all those, it's narrated in a number of different MP4 files. I've done it quite a while ago, so it's no Hollywood stuff, but it is at least a reference. Okay, so what we can then start with this morning is to go to Unit 8 here, vector autoregression. And we will discuss the lecture material is there, where we still have to specify a VAR and think about a little bit about the mathematics going in there and what are the math that we use in order to get those impulse responses out of it. And there's, so we have an application here that we will look at the example by Stock and Watson, the Stock and Watson article, and the associated data of that article. And then there's another example of a study that I was a co-author for, the monetary policy effectiveness in the face of uncertainty. So this data with this application is there as well under practical examples. So that's what we'll be doing, say, maybe until our first break. Maybe before we start discussing I'm just talking, and I don't ask, is there anything from your side? So by far, the majority of applications that we see using vector autoregressive models is in the monetary policy application. So many people want to see if there's an innovation in the policy rate. What will happen to all the different aggregates that we're interested in? Ultimately, how will that affect inflation? But also then, how about output or growth? How about investment, consumption, stock market, exchange rate? All those variables can enter that VAR. More recently, I've also seen it done with some climate applications. So that's maybe another nice application to apply to. But basically, any model where you know all these variables matter and they're interrelated somehow, but you're not exactly sure what are all those specific relationships. We can build this a-theoretical model and then use the impulse responses on the VAR to assess the impact of an innovation or a shock in one of the variables, or an impulse. That's what we refer to for those. So in terms of the theory, we apply this, as I said, when we have a number of simultaneous or simultaneous equation models is one way to look at the world. But in the macro context, unless we do simulation, it gets quite tricky to estimate those systems all at once. So for that reason, we then revert to either a structural VAR or a reduced form VAR. And reduced form VAR is what typically, if we talk about VARs, we will talk about the reduced form or the Sims VAR after Christopher Sims, who suggested this type of modeling. This is, as you can see, also the standard VAR. The reduced form VAR is derived from the original or the structural VAR. And the only difference between the two is that structural VAR also contain contemporaneous effects, a ZT in the YT equation. And the reduced form VAR will only have lags of YT and ZT in a two-variable system containing Y and Z. So we will think how it is estimated, and then it becomes useful, since in the reduced form VAR all those parameters don't have economic meaning. When we come here, it is we then use impulse responses or various decompositions. So what we will do here, practically, we apply it to that Stock and Watson example, which only contains 3 variables, which make it a nice application just to introduce the concepts. It's only to assess the impact of monetary policy. So the policy rate is there, the federal funds rate, the inflation rate, and the unemployment rate. In the South African context, do you think the SARB would be able to have a significant impact on the unemployment rate through any change in monetary policy? Will that be a great tool to use to address our youth unemployment of 70+%? Hardly. I think what the Reserve Bank can achieve is not. It can create a stable inflationary environment that's conducive to growth, attract investment, and through all those links, we hope to alleviate unemployment. However, if you look at this example for the US case, you can literally see over that sample period that an innovation in the policy rate have a significant impact on unemployment. Obviously, if the tools are such that we always work with a positive innovation, so it's always an increase in the policy rate, and then we see that that will then have a negative impact on unemployment, or it will make the unemployment rate rise. And then also, of course, there will be a causal effect. Monetary policy will lower inflation, but as soon as inflation starts rising, we also see that innovation prompts the central bank to later on intervene with some policy response. And the same with unemployment. If the unemployment starts going up, we then see that maybe in a next iteration, the central bank will then lower interest rates to alleviate the unemployment going up, to support the real economy. Yes?
I asked another question, but why wouldn't it work in South Africa?
It's not that it's statistically significant. If we look at those bands and the 2 standard deviation, if we look at the trend and the standard deviation bands around that, we don't see a significant impact. It might trend in the right direction, but there's not statistical significance there. Yeah, I mean, we should not keep trying, but I don't think monetary policy is our go-to tool for that. We have to focus on the fiscal side, what we can do with grants and skills development programs and those type of things. So it doesn't mean we shouldn't analyze that and see the impact, but the few VAR models that I've seen with unemployment it has never been a significant response. The notes here follow quite strictly those pages in Enders. I have summarized the mathematics of the identification of the system. So there's a few matrix equations to get the job done. So with the identification, the original way of doing it is to use the Koleski decomposition, where we put restrictions on the lower triangle of our matrix. You'll see how it's done. And then also, I can't remember if it's part of these pages or it follows after page 302. There's also the math there of how the impulse responses are propagated through the system. But I think for that, relying on the intuition is almost good enough for us here and now. There's also some other useful sources. The other textbooks that every textbook will have some reference to a VAR model, the Stereo and Hall book, the Gujarati book, the Waldridge book. Even the user guide of the software that you use can be helpful. The main theoretical article is the Sims article, and the Granger specifically for the Granger causality that features in the VAR. And this is now replication that I'm quickly going to skip over, just acknowledging univariate versus multivariate. VAR analysis is multivariate. So not a univariate AR or MA or a RIMA model. There's an example of a univariate model of exchange rates, just a random walk. Multivariate analysis, where we write y as a function of x1t and x2t, typically thinking of that steady state relationship, all the variables in current period contemporaneously included. And then, of course, we in this type of analysis, we make the assumption that there's a causal relationship from x to y and x2 to y, x1 to y and x2 to y. However, it can be more complicated like that. This x, these x's can be correlated, and furthermore, there can be contemporaneous and lagged feedback effects. Just an example of a multivariate structural model. So, yeah, as I mentioned, there can be feedback effects. So actually, there's another equation here where x1 also depends on y. That is possible. That's a violation of if you then only estimate one model. That problem we refer to as endogeneity. In Waldridge, we see this example of a very simple demand-side model. It's closed economy, so no trade with the rest of the world, no endogenizing of the monetary or the government sector. So the interest rate enters exogenously, the tax rate enters exogenously. How do we technically think about, how do we do that technical divide between endogenous variables and exogenous variables? If you see three equations and there's three variables here and it's functions of, you know, some will be included in other equations. The endogenous variables are strictly those to the left of the equal sign. If we do model simulation, we refer to those as our endogenous variables. However, so y is on the right-hand side, but we have endogenized it. C is on the left-hand side. This C has been endogenized. So if we simulate, we will, for the first iteration plug in maybe previous period, so it will be predetermined, previous period value, solve that, and it will be plugged in here. We will get a new y, we will iterate back, that y will be plugged in here, and so we will solve the model. But in terms of, if we think just a little bit outside of the block, is that tax amount, that taxes that's been deducted from income to give disposable income, is that really an endogenous variable? I mean, a proper exogenous variable. Income is earned, and everybody has to pay their share. So T is actually small t y, the marginal tax rate times whatever income. And this is a very crude model, so what should actually be here is disposable income of the households. And down here we have to say how disposable income relates to income. So we can also endogenize disposable income. But in this broadest, simplest sense, that T is not strictly exogenous. The tax rate may be exogenously be determined by the National Treasury. Every year they decide, shall we keep personal income tax rate as this with all the different categories, or shall we increase it or decrease it? And the same for corporate taxes if we go there. So that is a problem that arises. And then also at the same token that we can say, are those tax rates and interest rates really so completely exogenously defined? I can imagine an oil price for the South African economy here is kind of exogenous. We cannot do anything to affect the oil price. But our monetary and fiscal institutions, they don't really, it's not, they do look at where we stand in the economy. So setting that interest rate at a certain value is a function of everything else that's going on in the economy. And even government expenditure, this also looks like a very exogenous variable. But how exogenous is it? The government can only spend as much as in the first place is generated and earned through taxes and what they can borrow. So it is also a function of other things, so not so exogenous. So these are some of the challenges that we have when we model, which is then quite well addressed through simulation. And all of these models are simulated models. A CGE is a simulated model. A DSGE model is a simulated model. Models, behavioral equations like this, which are not based on the micro foundations, which we solve through, we estimate them using time series, and then we solve them using some of those model solver software like Seidel or Broyden or Newton-Raphson, some of those. And so just another way to think of that, an exogenous variable is one that influences the system but is not influenced by the system. So that's another way. That's maybe a more accurate way in terms of if we have to solve this model, these three variables are strictly our endogenous variables. Also, relationships are not always static. And again, this is referring to things that we did before co-integration. We would actually have consumption lagged in there. So those lag terms, so lagged income that can affect investment outcomes, when it enters an equation like this, we refer to those as predetermined variables. So by the time we arrive in period T, we have already simulated that value. So it's predetermined at that point. Or even how we observe the data. By the time we are in 2025, we know what the consumption, household consumption was for 2024. So if we want to estimate this as a system, to avoid endogeneity, typically estimating a system like that will involve some form of instrumental variables, which in a micro cross-sectional context present less problems than in a macro context. Because how will we find an instrument that's correlated with investment that's not correlated with income? Because all these macro variables tend to hang together and move together. And this is the connection point of Christopher Sims. He looked at the way modeling was done in the 70s, 60s, 70s, and maybe early 80s. And we had the Cowles Commission that suggested this is how we do it. So effectively what we do is, in this identity we have already restricted imports and exports. In this equation we have restricted anything else that could have played a role. So we have so all the variables that are not here, maybe government expenditure plays a role in this equation through crowding out effects. If we spend too much, that if government spend excessively, that will crowd out money that could be invested. So what Christopher Sims then argued, that this is not, he actually said all these restrictions that you guys place on a system like this is incredible. And not incredible like wow, incredible like not credible. So that was, and then his suggestion was, why don't we just use economic theory to decide what variables do we want to put in the model, and then let everything potentially affect everything else without any limitation. If there's no significant impact, there's no significant impact. But you don't close that road. That avenue remains open. Yeah, so this is the guy. And you can see if you do good work, you have to live at least for 20 or 30 years after the work. They don't give those post, what's the word, post of after you died, that you can't get a, is it post hominis? You can't get a Nobel Prize and then your family get up on the stage and they...
So with Albert Camus, like he wrote like the Plague, Stranger, etc. I think like a few years after he won the Nobel laureate for literature, he died.
Yeah, yes, yeah. If you, at some point, just as a matter of interest, I looked at all the recipients, and it's literally between 25 and 30 years before the acknowledgement comes. Yeah. Sometimes a little bit quicker, but for the most part, you can see he got the Nobel Prize only 31 years later.
Does that allow us to see if it has a meaningful impact?
I think so. Then you go on all those citation indices and you see. So just based on that, I cannot understand why Hashem Pesaran has not received if it's only about citation, because the paper most cited of all times in the top 5 or more journals is the system GMM that we use in panel, and yet you get so many people that hate the technique. You get so many people use the technique, and then others that criticize the technique. But just on citate, but Pesaran is one of 2 brothers, Hashem, and he has a twin brother. And they were the guys way, way back who wrote the microfit software, but I think later on he thought, no, I can do better things with my time than to code econometric software. And yeah, so he's been at Cambridge, but he's pretty much retired now. At some point he did some time at the Californian University. Yeah, so that's just beside the issue here. So what, and Sims called that paper Macroeconomics and Reality. And then there were other authors that wrote papers like Macroeconomics and a little bit more Reality. So there were quite a discussion around that. There's his statement calling those restrictions incredible and then offering a solution. So that's also, so what about our large scale models? Now we can't do that. But Pesaran has that global VAR project where they built VAR models for their project includes 33 countries. We have the VARs by itself, and then there's interlinkages between the country VARs. So what is the VAR model about? There is no a priori before the fact. We don't before the fact say consumption and investment and income will be my endogenous variable. Every variable that you include is essentially also a endogenous variable. That's why when we did that co-integration test and we want to include a structural dummy, a pure exogenous variable, then we don't enter it as one of the equations, because then it will become part of the VAR system as an endogenous variable. And we can't claim that the global financial crisis or the COVID crisis is a function of the other variables. That's a pure exogenous event. So we include that in the error correction VEC-M literature as an exogenous event. So every endogenous variable can then be explained by all other variables in the system. So we say vector because if we have 3 variables, federal funds rate, unemployment, inflation, we have a vector of 3 variables Autoregressive, because we're going to lag every variable multiple times and put that the same information set on the right hand side of our endogenous our 3 variables in that system. So it's a natural extension under the premise that everything can affect everything else. So it's useful to describe dynamic behavior in economic and financial time series. So when we're not confident that a variable is exogenous, we treat every variable, all the variables symmetrically, so all of them can be on the left-hand side. What we discuss here is the application of a reduced form VAR. So in this section, we don't discuss the structural VAR. Typically in our more advanced course, after I've done this, then Retiro would spend a day or 2 on the structural VARs, which is used alongside the DSGE models. So what's the difference between a structural VAR? A structural VAR contains, it is possible that the variables can affect each other contemporaneously. So there will be a ZT in the Y equation and a YT in the Z equation, whereas the reduced form VAR has only dynamic terms. And this will be a VAR of order 1, since we lack all the variable 1. It's a 2-variable VAR of order 1. So structural VAR, in a structural VAR, the parameters have economic meaning. In the reduced form VARs, we cannot attach any economic meaning to the parameters. So that is where we start. The bivariate system of a structural VAR, if we can keep it simple and just use 2 variables and 1 lag on each variable. So both of these, you can see, are assumed stationary. Those 2 error terms are well-behaved white noise error terms, assumed, it may not be, and they are uncorrelated. They are not, those 2 error terms are assumed to be uncorrelated. So those are the so that constitute our first order autoregression VAR model. So both can affect each other contemporaneously and with a lag. Also, how we are going to use those error terms are then seen or used as the innovations or the shock or the impulses to see what will be if we shock Y. And shock is sometimes, it sounds a little bit negative, so innovation is almost better if there's a positive innovation in the interest rate, or there's an innovation in the unemployment rate. Something caused the unemployment to rise. When we test that, this is where we will place that innovation. A 1 standard error innovation in that variable, we will add to that error term,
Sorry, Prof. So does innovation just simply mean intervention or change?
plus a little number.
Okay. So it's an incremental.
It's like the policy rate innovated, increased by, but it will now not be 100 basis points. It typically you can specify 1 standard deviation of the series or 2 standard deviations of the series or whatever the case may be. Unless that variable is 0, or if that variable is not 0, that parameter, then a shock to Z will obviously cause a change here, which will then affect Y. So if that is 0, a shock to Z will not contemporaneously affect Y in the same period. In the same way, if this parameter is not 0, so a shock to Y there will change Y here, and that Y will then affect Z. So there will be a contemporaneous effect too. So who can read this line as well as you can read English? Can you, if you look at that, can you see this?
Yes.
Okay, great. Sometimes we get students from philosophy, so they don't have to do math.
It's much better that becomes philosophy.
Yes. But finally they all manage, and then when they write papers, they write so well. Sometimes I say, how come you write so, the arguments are just so integrated and nice, and then I hear, no, I did philosophy up till my 3rd year. Yes. So if there are any philosophy students here, how we multiply that matrix is simply, I had a lecturer when I did matrix algebra in my 2nd year. He used to write this on top here. So then this will be the result, and he will say that times the y1 as the yt plus the beta 1, 2 times the zt goes there. And that's an easy way to see it always. This is a 2 by 2, 2 rows, 2 columns. This is a 2 by 1. And we can only multiply a 2 by 2. Then if it has 2 columns, this one will have two rows, otherwise we cannot multiply it. So it's basically that we go from here to there, because then we can in a very compact fashion just have a 10 variable VAR, and we can have it can have 12 lags if needed. So what we do from this step to this step is just to normalize on the y, get the y on this side, so we just take that on the other side, and then it becomes minus a b1, 2. But still, so this is our structural VAR, and this is just the matrix notation of our structural VAR. So how do we get to the reduced form VAR? So reduced form VAR, what we want to get rid of is the current period y and z. So how we do it, we just call that matrix B. It's a 2 by 2 matrix. We call this column vector gamma. We call that square matrix gamma 1, and so forth. And what we want to do is to get rid of the B. And how do we get rid of the B? Is by just taking the... that's almost like if it was a scalar number and the number is 4, that will be 1 over 4. And that will give 1. In terms of matrices, taking the inverse and divide by the inverse then gives us an identity matrix. That is a square matrix with 1s on the diagonal and zeros otherwise. So then we have this, and this now looks like a reduced form equation. So that's what we want to do. So to summarize, we move from here to here, and this is now what we're going to do. Just a side note, in this case, we have to estimate 10 parameters. So the 1, 2, 3, 4, 8 parameters up here, plus 2 variances, and they are independent, so no covariance necessary. Down here, we estimate 9 parameters, so the 6 parameters, 2 variances, and 1 covariance, because now they are no longer independent. The one has elements of the other one in it. So the difference is basically that there is still some economic theory in those relationships, whereas in the reduced form VAR, all that we can claim is that we used economic theory to identify our variables that we put in the VAR. So here you can see how those error terms of the reduced form VAR are actually functions of the original innovations in Z and Y, and also the parameters of the structural. That's why once we arrive at the reduced form VAR, it's like we have scrambled the eggs to get these parameters. We cannot unscramble the eggs to go back. So they relate like that. So that means the correlation between the two, because this one is for Y and this one for Z, the correlation is non-zero. Only in the special case that there's really both variables affect each other with a lag can we claim that they will be independent, which is hardly the case. Many economic variables that are related will affect each other, or at least one of them will affect the other one contemporaneously. So if in the literature, if you look at the paper, we will just write, it will most likely be that we write the VAR as this, and then just say that my X vector contains interest rates, inflation, and output or growth. So how do we approach that? We determine which variables to include. At the outset, maybe you can say, I want to include stock market outcomes, exchange, what happens in the currency market, a whole lot of things, and finally just streamline a little bit and say, let's focus on prices, interest rates, prices, and the transmission to output or production is through consumption and investment and output. And that's it. But anything that you're really interested to see if there is an impact, we can include in the VAR. It is just the more variables you include, and the more lags you include. So even if you just estimate a six variable model and it's quarterly and you decide to include P or 4 lags, now you have 150 parameters. That's a large demand on your system. So that means you may want a sufficient number of observations to allow for that and not run out of degrees of freedom. Now, this discussion, I think we had it a couple of times. What is the right number of lags to use? A good question. Not a very simple answer. Because and all of these are functions of the log likelihood, which is essentially how good the model fits the data given the parameters. We can see these are negative functions of the log likelihood. So the lowest value of all of these will tell us which order, how many lags will fit the data best. And the top one, the Akahiki, most often will tend to suggest a larger number of lags. It will tend almost to overfit the model. Whereas the Schwartz criterion, you can see when we take the log of t, if t is large, the log of 100 is a much smaller number. So it will penalize the system less so it will give a simpler, more parsimonious model, if that's what you're after. If you're after more accuracy, you may want to stick with that one. But just in a practical terms, if you then look at your impulse responses, there's a lot of noise in there. It's not smoothly. So sometimes it's better to trade that off and go for a shorter lag. The Annan-Quinn will slightly penalize it less than, but what I've seen in a practical sense, they are most often the same. But there's almost always a discrepancy. Akahiki will tell 6 or 8, and then Schwartz will suggest 2. So there's absolutely no right or wrong here. There's maybe more correct, less correct, but it depends on the application. What if we get 3 and 2? That's so close. Then probably start with 3 and see if you're going to end up estimating a vector error correction model. If anything goes wrong along the way, like your error correction term has an insignificant parameter or a positive value, but if you take 2 lags and everything works well, then 2 lags is obviously the better choice. But for the most part, I think sticking with the default would be the first avenue to test. But there's not that you can say you absolutely must go for the most number of lags. I've heard that people doing a lot of this work, they will say if you have a monthly model and there are seasonality in, then best to go with the 12 lags, for instance. So, however, as long as you can argue that well. So this is in eViews what the output will look like. So if we estimate this 3-variable VAR and we allow for up to, so since it's a quarterly model, you can allow for tests for up to 12 or up to 8. And then for the log likelihood and the final prediction error measure, we will, for the log likelihood and the final prediction error, those will be the largest values will be, no, the lowest value here, the largest, no, also not. But these we don't use in practice for those. We definitely want to look at the lowest values. And don't be fooled. It's actually, you know, sometimes the software do too much, like parents for their children. So I have asked students, I've given them the output and said, make the model selection. And they said, there's no VAR here because there are no asterisks. That is, you see why softwares like this get critique? It's because we don't know what we do then. So yeah, so if there's no asterisk, just go through and see which value is the lowest, and 3.45 is the lowest. Sometimes they are negative, but then you still go on the numeric scale and select the lowest value. So we want to find that trade-off between over-parameterizing the model, overfitting the model, versus if you drop too many lags, maybe you have an inaccurate representation of what you're testing. So once we have decided on that, we can, what is used is actually simple OLS because of the fact that it only contains predetermined variables. The error terms are assumed serially uncorrelated. There's no zero correlation in any of the two residuals. Then we can estimate because those, what we will find are consistent and asymptotically efficient estimates. Of course, if we have zero correlation, it's no longer the case. But that we typically fix by extending the order of the VAR. So if you in the end find zero correlation, it may be an indication that you should have worked with a higher order VAR. So it's quite important that you work with stationary variables. That's what the literature keeps on telling us. Although if you look at the literature that is currently, there's a whole lot of work done by Pellegrino and other authors, and they estimate VARs in levels. Without saying why they do it, the only reason I can imagine is that they use bootstrapped errors so that there's not that problem of the biased standard errors. So can the structural VAR parameters be recovered? Only if we place appropriate restrictions. And that again is as difficult as doing it in the VEC-M, as we will see. We have to, we throw all the spaghetti at the wall and then we have to, I don't know what, but we put all the variables there, and then we have to say, okay, in this bag of variables, these are related in such and such a way, and I have another equation here. But here we just in the reduced form VAR world. So how do we now identify the system? So effectively, the Koleski decomposition will go to this beta parameter matrix, and in this case, the lower triangle is only one element. If it's a 3 by 3, there will be another one here, so we will have 3 zeros in the lower triangular part. So we will say that having zeros down here, it will be an upper triangular matrix, but we put the restrictions on the lower triangular part of that matrix. So if we do this, what we allow is that Z can affect Y in the current period, but Y cannot affect Z in the current period. We blocked it there. It's almost as, I don't know if you've seen little clips like this, where the farmer has his sheepdogs, and then they all sit there and they're so eager to go and work, and the sheep are there, and then he calls the first dog and the dog runs. And the others are like, they wait for their names, then they go, and then the third one goes, and so. So this is almost like calling the first dog Repo, you go and do your thing. And who shall we call next? Consumption, production, unemployment. So, and each time, so from the most exogenous variable to the least exogenous variable. If we have more variables. In this case, it can only be repo and inflation. So we let repo go first, affect inflation. Inflation can affect back, and over time, if inflation it will come down, and if it starts rising again, interest rates will probably be adjusted again. So that's the idea of this. And then I just have like 2 slides or so trying to make it a little bit more clear how that happens. That Z and lagged Z can affect Y, but only lagged Y can affect Z. If you look at this system here, that is this is the structural VAR. This is the reduced for. No, it's just rewritten. Let me just see. That is multiplied out. This is multiplied out. So that's equal to this. So in this case, we can see that Z can affect Y and Z. Z will affect Z, and Z will affect Y and Z. And we can also see it here in the second equation. Z will affect the dependent and then will affect the first equation. How do we decompose? How do we do that decomposition? For a bivariate VAR, we only have one restriction. If we have n variables, n squared minus n over 2. So here for a bivariate VAR, 1 restriction, a 3-variable VAR, 3 restrictions, and then for a 4-variable VAR, 6 restrictions, and so forth. In the 2-variable case, for instance, inflation and repo rate, we can then, if we then place innovations here, what we will see is that when we look at the result, we see that this will be the result in inflation given an innovation in the policy rate. So effectively it comes down, but what about this? Why do we often see that response? We refer to that as the price puzzle. Because interest rate goes up, but it takes a while, it takes a full quarter for things to turn around, for hitting the brakes and start consuming less. And sometimes it can take even more than one period, 1, 2, 3 periods, because agreements are in place, raw materials have been ordered, you have already hit that order on the online shopping, you know, all of those things. It's difficult to immediately, for prices to immediately start reacting. And the thing is, we see that even here, how we interpret this, we have this 95% bootstrap confidence intervals. We can only claim that the impact is down and significant when both of the bands are on the same line of the zero line. So when is it really actually, it only starts being effective from this point onwards. So literally 6 periods it takes for that inflation, downward trend in inflation to be statistically effective. I've seen a couple of policy papers that claims it takes 18 months for monetary policy to really work through as they would like it. Is that right, Kuletsu? Yeah. So this is like after 6 periods or so, the blue line is below the zero and both the bands are below the zero. Obviously, we can change this to a different number, like 90% confidence interval or whatever the case may be, and relax it that way. So that is now just innovation in a bigger system, just focusing on one result. If we innovate the repo rate and what happens to inflation. I think it is tea time. Is it? Not yet. I'm learning nothing here.
We are interested.
So now how can we, that's just like a glimpse of where we're going with this. How can we use this impulse response functions to get an idea, obviously given this time frame of data that we have, on average over that time frame, an innovation led to this effect or that effect or whatever the case may be. So the reason why we place the Kuleski decomposition restrictions is because the VAR is under-identified. And the mathematics that we show there by placing restrictions on the B matrix is how we get it done. But all of that happens in the background. The limitation or the caveat of the Koleski decomposition is that we have to order our variables from most exogenous to least exogenous. So the farmer must call repo first and then the other dogs. In the generalized impulse responses, and we don't show the math here, but the ordering does not matter. So that's why you see in a practical application, most papers will use generalized impulses. These orthogonal set of innovations means independent set of innovations. So, but in a practical sense, if we've ordered the variables as we mostly would believe, policy rate first, and what would be the first? Maybe it will lower inflation by lowering demand. So consumption will be affected first through the interest rate effect, and that eventually will lower inflation. Investment will be affected negatively because borrowing rates are higher. And that will then affect inflation. So whether inflation goes there or production goes, next in that, that's probably, you see, that's where you also, your economic theory comes into play as to how you order that with the transmission, how exactly, what are the theory of all these transmission mechanisms. Typically, higher interest rates will also harm the stock market because it's just more expensive for companies to borrow, and higher interest rates, by definition, may cause more uncertainty and negatively affect the stock market. How about the exchange rate? What are these? There's also different transmission mechanisms there. If interest rates go up, maybe it will attract some inflows, but which can strengthen the currency, but there can be opposing effects as well. So typically the exchange rate is also a variable that's not so clearly significant. We don't see a clear significant impact of monetary policy. Am I right, Koletsu? It's a little bit dangerous if you start talking policy, explaining the techniques, and you're not a policy expert, right? It's good. I have to put like a disclaimer somewhere. And the variance decomposition is not such a graphic depiction of the impact of changes, how all these variables affect each other. However, we can see typically an exogenous variable will explain most of its own forecasting variance. Whereas for variables that depend on other variables, you will see that, and maybe at an increasing rate, explains that forecasting error variance. So we will see that in the example as well. Typically, as a side issue, when we do a VAR, we can also look at the Granger causality. And sometimes the Granger causality test is just used on the side to test whether we have a univariate or a bivariate causal relationship. You see it sometimes applied in panels in the energy and production relationship. What is necessary? Do we need first to produce more energy and that will help us to produce more? Or is it we have to produce more and that will create resources to expand the energy sector? So there are all these hypotheses that we then test, and we have really nice panel causality tests that can accommodate non-stationary and heterogeneous panels. But again, not everybody is a fan of a Granger causality test in terms of reviewers of journals and so. There's a very nice time-varying Granger causality, a technique by Rossi and Wang. And if I'm not mistaken, they both female. Barbara Rossi, I forgot what's the lady who Miss Wang is, what's her name? That is really a nice one that we can see period by period. I'll show you tomorrow an application where we think about inflation and inflation uncertainty. If you think about prior to the where we set the inflation target, prior to inflation targeting, which was 2000, we did see that higher inflation caused higher uncertainty, and in return, higher uncertainty caused higher inflation. But during the inflation targeting period, that completely broke down. And now we see, because of transparency, it's not that if we see some uncertainty that inflation goes up, or if that inflation goes up, that it creates panic and uncertainty in the market.
Sorry, Prof. How would you define uncertainty in the model?
Using a gauge term in a gauge model, or calculating a realized volatility. Okay. So that we discuss that tomorrow. Yeah, so that Rossi and Wang method is really nice to use, and there's also now a quantile causality test by Ms. Wang and Rossi and another author. I just saw it in the Stata Journal last week. This one. Where is it now? Shout stop. Okay, I could read it there. Hey?
I'm just thinking, so if we think from a component, let's say meat in the CPI basket, right? And I want to see how shock to beef prices will affect that overall component. Would that be improper to do, like going forward, like if I'm looking at forecast, like because of the foot and mouth disease, for example, I want to see how much the variation in changes in beef prices will affect overall meat prices within.
Yes, I think it's a good idea. The sample that you have, were there occurrences of foot and mouth disease? Yeah. Just as long as we keep in mind that those impulses can only deal with what was in that historic sample. You don't have any way to do typical what-if scenarios and things like that. But if there's that relationship, yes, I'm sure. I think it's a good idea to use this as another way to look at the problem. And also, if you then look at the variance decomposition, you can then see maybe that beef consumption had more or less how much it matters. Say even if it only have like a 10% forecast error variance, but then it's increasing to 15%, or it's 15 and then it decreases to, you can then argue at longer horizons, then it matters less, or yeah. So what I want us to do is to maybe hands-on do the Stock and Watson example together, so that in front of on your screen you can have those impulse responses so that you can see clearly. So, but maybe let us take our tea break, and when we come back, we do those impulse responses, and then we just look at the interacted VAR, the Pellegrino approach that is in that other paper with the uncertainty. Thank you. So let's take a half an hour break. So we come back 5 to 11.